Okay, for the record, all students are here, although Joshua's status is away, but he's here. Okay. Let me know if not able to see the screen, or you cannot hear me, just let me know. Okay. Two-block equation done. Then there's a diagram under question 7 also. Please text me. Okay. All right. Now, for the diagram that under question 7, you see there's again combination of sink and source, and you see the streamline. That source coming out, and then the sink will absorb whatever come from the sink. It's like a magnetic diagram, but this one is a water or air. So source and sink, you will see that the arrow represent each type of this. So this is the equation that we developed just now. So stream function or streamline equation equal to negative m. Again, this one is the mass flow rate per unit length. Right, it referred to definition in slide 1 for today. So 2 pi divided by 10 inverted 10, and then the value inside this term. So for if the a distance, meaning the distance from the center is very small, all right? So if the a distance is very small, what does it mean? It means that if you look at the diagram above your handouts, the a is very close, means these two are very close. Then the value of your 10 will be very, very near to the constant value that you have. All right, so if your a is very small, then this term you can rewrite as this term. So whatever the constant value is inside the 10 column here, then you can just rewrite. Then you rearrange, take away the similar component, 2 cancel, and at the end you have negative m divided by pi and ar sine theta divided by r squared minus a squared. Okay, all these terms still refer to the diagram under question 7. These are the characteristic or that when we define a duplet. So these are the two things that we will see. So how this duplet can be formed is that number one, you have the source and sink close to each other. Okay, you have the source and sink close to each other, and then the strength of m, you increase the strength of m near to infinity. Means the important point here is you increase the m value here. You increase the m value here in the equation, and then because the two source and sink is very near, so this one you can near to 0. So the equation of this one, m very large, a very small, and a very small, then you have the r squared r you can cancel, and then this one you can further simplify. And this one is ma pi remain constant, ma pi, meaning that all these are remain constant. I think the product, this one means ma divided by pi, because ma divided by pi remain constant. So you will have this after all this assumption, this equation reduced to stream function equal negative ma sine theta divided by pi r. Okay. Stream function equal to negative ma sine theta divided by pi r. After all these assumptions, after these two statements, then we get a stream function for duplets. Okay, then we know that MA divided by pi is the constant value. M is a constant, A is a constant, pi is a constant. So we combine this one in another parameter called K as a constant. Then we only look at the stream function, relationship between stream function and the theta and the R. So this represents a relationship between your streamline function or stream function and angle and the R. Okay. So again, I think this one is the typo error without the divide. Huh? Yeah, the divide sign is missing here. All right. And for doublets, MA divided by pi is the strength. MA divided by pi equal to the strength for doublets. Just now we have strength for vortex. Or no, for our source. All right. So now if we have a doublets, then there's another definition for the strength. And another term for your velocity potential will be equal to MA cos theta divided by pi r. So again, you can simplify MA divided by pi with the K. So if you compare equation for doublets, your equation, you have two. One is for streamline, one is the velocity potential. One with a negative sign, one with the cos and positive sign. So we have a few set for different scenario. So if you have a single sink, then you use the single sink equation. You have a sink or source, individual one, then you use the individual equation. If you have a doublets, means you have a sink and source, then you use these two equations. Okay. It's quite direct for this chapter. You look at the scenario, you just pull out the correct equation, then you just apply. What is maybe challenging for you guys is the differentiation and the integration part, and also the trigonometry part on the conversion of angle. Okay, now it's just a presentation of the diagram under question 7. This diagram, if you have this statement, then you will get this phenomena at the end. Meaning, if the sink and source getting too close, you will see that the pattern that you have will be in this form. Right, on the top, you have anti-clockwise circulation. Right, on the top, you have anti-clockwise movement for the streamline. However, on the bottom half, you have anti-clockwise. On the top, this is anti-clockwise also. Okay. And you'll see that there's an arrow in the vertical horizontal axis. You'll see that arrow is from the left, from the right to the left. It's an opposite direction to our normal x-axis definition. Right, so you have a negative sign here. Right, let's just explain the diagram that you have on your hands out. Okay, then on your page number 6, the next page, it's just a summary of what we learned just now. So you just have a read, and maybe the table is very useful for your final exam. All right, so just look at this diagram and then plug in the correct equation to analyze your problems. Right, each of it we cover just now. Okay. Now we look at stress deformation relationship. So again, all this equation that you see on the screen is given in your hands-out. So you can see that the stress is linearly related to the deformation. Okay, this one I think you learned in your static module already, static and dynamics. So you have the stress in x, y, z, and then this one is the u, v, w, and mu. This one is the viscosity. Right. So yeah, this important for question 8 is to stress that the stress force or stress load is linearly proportional to the deformation. Right, on the right is on the shear stress. Left is all these are normal stress. On the left is normal stress. On the right is shear stress. So if you're not sure what is normal stress, shear stress, you need to go back to the static chapter or static module to look at what is shear stress definition, what is shearing stress or shear stress definition. Okay, and the top two equation, two set is for the Cartesian coordinate. Is for the Cartesian coordinate setting, because you see x, y component and z component, so you have a Cartesian coordinates. While the bottom two set, you see r theta and z. This is the cylindrical polar coordinates set. This is the cylindrical polar coordinates for the second set here. Okay, just a side note. Yeah. So just a concept. So for nervous stroke equation, the name is very bombastic, but the content itself is from the second Newton law, F equal to ma. All right. So when someone asks you, when you come to your final year next year, if you use simulation, most of the time you will come to nervous stroke equation. So the panel will show us you what is the fundamental of nervous stroke equation, or explain what is nervous stroke equation. So if you're able to explain like nervous stroke equation, the content is about second Newton law, then the panel will know that actually you know what you are talking, right? And so this is just explain what is second Newton law, F equal to ma. So A is acceleration, m is mass. And you have the nervous stroke equation in your hands also. So I won't want, no, you don't need to like copy all these equations. So I already copy and paste into the hands also already. So you have these three types of equation in the for the nervous stroke equation. So what is important for nervous stroke equation is that the structure is quite similar. What is different is, for example, the x direction. X, on the top, on the left hand component is u, or is it u because it's on the x direction. And then on the right hand side is del x, gravitational force, gravitational acceleration on the x, and also deformation in the x component u. Y become v, g, y, v, z become w, and then gz w. Yeah, this is the different structure lah, but in general they are quite similar, only change the velocity component and the gravity component. Okay. Then in your question number 10 and number 9, you still see some equation, and this one is in the r and theta radial coordinate component. You're still seeing these three in the hands-out also. R direction means you'll see in the R, VR on the left-hand side. Right-hand side also you'll see the R component. All right. Only different is the Z structure. You will see a bit different in the structure. Right. So this is just an observation, and all this you can copy from the hands-out or from the textbook. All right. The objective here is to let you know that at least you've seen what is Navier-Stokes equation before. Right. It looks very complex, but again, it comes from F equal to ma, and it derived based on the reference coordinate that you are choosing, either Cartesian or radial coordinates. All right, then question number 10. Question number 10 is ask you how the Navier-Stokes equation for flow between two horizontal plates can be formed. All right, so I think this one you can look at my screen later on. I just want you to focus on the screen so that you understand what we are talking about. So we are talking at two plates here. Plates means a flat plate. We no longer have a cylindrical plate, but we're looking at fixed parallel plate, which is a flat plate, top and bottom. And then we have a middle reference point here. Our reference axis is in the middle, and all the flow to the right is along x-axis. This is y. On the top is y, and z is in this direction. Right? It's come up from the screen. U represents small u represent flow along x-axis, and we have a gravitational force pointing down. Right? Because in the Navier-Stokes equation that we see this now, we have a gravitational force, right, inside the equation. That's why we include that one. For derivation, for laminar flow, fixed parallel plates, steady flow, we don't have velocity in the y or z direction. Okay, assumption that we don't have flow in y direction and z direction, which means give us our small v equal to 0, small w equal to 0. V and w is our velocity vector. One is in y direction, one is in z direction. And our continuity equation, m dot, will give us the change of u divided by x will be 0. Means there's no acceleration inside this pipe. So this is the equation we use. Del u, del x, del v, del y, del w, del z equal to 0. Steady incompressible case again. No changes in z direction for our u component. Steady flow means, if you write mathematics, means del u over del t equal to 0. Steady flow means no acceleration, because if you take velocity divided by time, you get acceleration. A equal to u divided by t. Right? And if you look at gravitational component, gx is 0, gy we have a negative g because it's going down, negative because our reference point is positive upwards, because our g going downwards we have negative g, z equal to 0 because we don't have, our gravitational do not go to z direction, it's always pointing down on earth. So you reduce your equation, reduce your Navier-Stokes equation, meaning just these three very complex equation. After the assumption that we state just now, it reduced to very simple equation. reduce to this one. Everything on the left hand side becomes 0, and right hand side only have negative del p divided by del x plus mu and differentiation square of our u and refer to our y component. Okay. And then further for this is for x component, y component, and z component. Because our Navier-Stokes equation, we have three direction, x, y, and z. So we have 1, 2, 3 equation. Again, later you can copy all this for my slide later on. Right? I will upload on the team later on. So stop me if not able to understand what I'm talking about. So it's just explanation how we reduce the Navier-Stokes equation based on all these statements on the right. Then it become a very simple equation. Then, because all these are in the differentiation form, you can integrate to get our pressure component and all this. Right? Because you integrate your differentiation component, because you have pressure and y, pressure and z here also, then you'll get pressure in the term of negative rho gy plus the constant value. Constant value. This is your C. Right. Then this one is just rearranged to get the integration. So you pull this one to, because you want to look into this term. So we pull everything. This one become positive, negative on the right hand side. Put to the left become positive. Put your mu to the left become this one. So you integrate this term towards y. You integrate again because we have a double differentiation. You integrate 2 times to get your u. Right? The process is always want to get the component of our u. And then these two can give you pressure. This one, the x component, give you the velocity at u. That give you this equation after you integrate 2 times. Constant value later on. So all these are the statement that we have. Because this is the u that we integrate from the x component just now. U equal to 1 over 2 mu del p over del x y squared plus constant value. All right, again, this one come from the Navier-Stokes equation. After the statement that we simplify this one. And then for the y and z component, we integrate, we get this equation. Focusing on the pressure. However, for the x component, we rearrange, we get the u component equation. Integrate 2 times to get the u profile, velocity profile inside the parallel plates here. Okay. And then we put in the boundary layer, boundary condition to find C1 and C2. The first one is when the 2 plates are fixed, our u is 0 for at the location here. All right. When our location as h here, this is positive h, this is negative h. Because our starting point, initial point is at the center. So going up is positive, going down is negative. So either way, positive h or negative h, at this location, your velocity is 0. There's no velocity at this region. You substitute this boundary layer in this equation, you get your constant value. All right. So when your C equal to 0, your C2 equal to some equation. Mean your C1 equal to 0, your C2 equal to sum of the equation. Then you substitute your C2 inside here. All right. Substitute this one. Okay, you substitute inside here, you get this equation. You rearrange, you get differentiation part. times y2 plus h2, right? Some component, one component, second component. And we know that velocity profile from here, this equation is a parabolic, because in the previous slides, when we plot the velocity profile, you know that when you have a y squared plus h squared, this is a parabolic equation. Which is we see in the circular part also. Right? That's why we see this term. So this equation is a velocity profile that derived from the Navier-Stokes equation, and then plus the assumption that we have, simplify, we integrate 2 times, we get this one. And then the Q, volume flow rate Q, pass through the pipe, pass through the plate here given you by this integration relationship. Q equal integration of h to h u dy. You substitute what you have, your u just now, inside this equation, right? Focus on the strategy of the derivation rather than the mathematics model. At least you understand what is happening, right? What procedure that we use, right? So you just substitute back your u, you'll get this form. Simplify after you integrate, simplify, you'll get this term. And just need to note is that the pressure gradient is negative because the pressure decrease in the direction of the flow. Because if in the channel here, your pressure must be high on the left so that your flow can move to the left, because high pressure always move to the low pressure, right? So you have a negative del P there. The gradient, you have a negative. Okay. And then you pull out the relationship between del P, pressure drop between 2 points. So del P divided by L. This is just a development of mathematic order. Delta P divided by L. You take the delta P divided by L, then you put in the differential form. Negative. This is a pressure gradient. Del P over del X. You rearrange this one. You can transform this equation in the differentiation term. You can take away the differentiated term, put in the quantitative, means you can measure delta P term. So from here, come to here, based on this assumption, this mathematical model, you substitute inside there, you get your volume flow rate in 2H3 del P divided by 3 mu L. Okay, so this is just a application of Navier-Stokes equation to get the volume flow rate Q. And this Q is very small q, not a big Q. Small q, that means that your volume flow rate is in the unit of width in Z direction. In the unit of width, right? Means your unit will be m squared divided by s. Your unit for Q will be m squared divided by s. All right. So this is just a further derivation for your u, for your velocity v. Yeah. So we take the average velocity. Average velocity in the plate from experiment, we get the relationship v equal to q divided by 2h. You substitute this equation because this is q, we want to put in the term of v. So you rearrange this one, substitute inside there, rearrange, you get v equal to negative h squared del P divided by 3 mu L. So again, from q, substitute this relationship, we get v. Yeah, interesting is that just a reminder, we always have a maximum velocity at the middle of the plate, middle of the channel, which is here. If you look at the velocity profile, we always have a maximum here. Always have a maximum here. So when our y equal to 0 means at our origin, our center line of our channel. Okay. So this statement just to allow us to further simplify our velocity profile equation, because at the center, y equal to 0, we can further reduce. Our equation become the equation for the Umax for the fixed plates, parallel plates. This is not a cylindrical plates. This is a parallel plates. So our U maximum for parallel plates will be given Umax equal 1 over 2 mu your velocity gradient times the h square. And by mathematics, if you substitute or you do experiment, you will know that your Umax equal to 3 divided by 2v. Okay, if you put your Umax in the v term, then you'll get 3 divided by 2v. It means that if you have a velocity, your Umax is 1.5 times of the velocity that you can measure. Okay. This is number 12 already, yeah? Number 12 in your tutorial question. We start to look at circular tubes. Just now is parallel plates. This is a circular tubes. So circular tubes, there's a new name for this type of flow inside a circular tube. We call it Priscilli Law, Priscilli Flow. This name we also saw in our chapter 3, where we have a Q for this kind of flow, for laminar flow, right? Q equal to something. So there's a law for laminar flow inside the circular tube. And this kind of flow, we call it Priscilli Flow. So the blank that you need to fill in is the Hagen-Priscilli flow. It's very important. At least you hear before, or you heard before this name, Hagen-Priscilli flow. It just means that you have a laminar, incompressible, steady flow inside circular tube. Okay. And then this one is question 13. Question 13, it asks you to explain how the Navier-Stokes equation can be developed into Priscilli law or Priscilli law equation. This also you just watch, you just pay attention to the screen. You can copy all this equation later into your handouts. So you have this diagram in your handout also. So we are now looking at a cylindrical pipe with the center reference, our reference point axis or is inside at the center of the pipe. Going up is y, along x-axis is z, and then we have a r direction. Okay, r direction, and our have a point with velocity in z. And then we have a gravity pointing down. So how do we develop the equation for this kind of pipe? So again, there are some assumption before we develop equation. So we assume that again, flow that parallel to the wall here will be 0. So VR0 means that our velocity at here, our maximum R here, will be 0, and there's no angular velocity, V theta equal to 0 means at here there's no movement, so everything is 0 here. And continuity equation reduced to del V divided by del Z here. There's no acceleration along Z axis. There's no acceleration for your velocity because we refer to this diagram. Your velocity is along Z axis. So if you have a steady flow, means there's no acceleration inside the tube. So there's no change of velocity here. So we can write this equation. Steady asymmetric flow, so we don't need to define our Z in the function of time and or angle. So equation, Neversole equation reduced just now the radial equation, the 3 radial equation. That one is above question 10 in the handouts. So the 3 equation reduced to these 2 that you see on the screen here. Then you further reduce it, further rearrange it, and you have all these equation. So the first one, second one, third one. So all is 0 on the left, and then you rearrange. So for laminars, circular tubes, inside circular tube you have these 3 equation, and these 3 come from Neversole equation. And how we reduce this one is based on the assumption that we mentioned just now. And again, all this you see differentiation. Differentiation, you integrate, you get pressure. Differentiation, you get pressure again. You get pressure equation with a constant value. And this one, you have a velocity here. So we integrate, and then we'll get velocity in Z direction, in this direction. Okay, you integrate, you rearrange, then you integrate, you put in the boundary condition to cancel out the constant value. All right, like what we did just now for parallel plates just now. All right, and you get your C2, substitute in, you get this term. So again, you see if you make comparison with the parallel flow, the structure is quite similar. Just now you see H, now you see R. Just now, the parallel plate, this one, y squared plus h squared. Now you see r squared plus r squared. And again, if you have a square minus square something, it's called parabolic distribution. This is a parabolic distribution equation. Okay. And yeah, this is all this. The next few slides is just a mathematics derivation, so you can read from the slides. Next one, we're interested to find the Q. Q, you take the velocity times the circumference and the change of dr with this one. dr is the change of r. All right, so Q, we know that Q equal to VA, V velocity times cross-section area. You take the circumference times the dr, you get area. All right, then you integrate with the dr. Put in the u term, the z term, the vz term that we defined just now from the Navier-Stokes equation. Put inside, you get your Q, rearrange, you get your Q, and then pull out the assumption to get the gradient, pressure gradient, delta P divided by L. Because this one, differential P divided by del Z, we can't do anything in the experiment. So in experiment, we can measure delta P and L. So we need to change this mathematical model in the way that we can measure. So after we have this equation, substitute in your delta Q equal to pi r 4 delta P divided by 8 mu L. This is called Priscilli Law. So this is, you can check back, is the same like what we learned in chapter 3. We have one law called Priscilli Law for steady laminar flow in circular tubes. Okay, Priscilli Law only apply for circular tubes. And for flat plate, we use this equation. Flat plates, we have small q per unit length. So we have this equation. So far, textbook that I read, there's no name for this Q component. Okay. V also, we can put in this term. So in experiment, we know that V equal to Q divided by pi r square, means Q equal to VA. So we know that area is pi r square. So we just rearrange, put this term inside here, and then rearrange, we get our velocity. We know that velocity always maximum at the center. So if you want to pull your Z, your parabolic velocity profile equation, you can further reduce because you're at the center, R equal to 0. So R is 0. Your left-hand side component becomes Vmax. So you only have negative R square and your pressure difference, del P divided by del Z. And recall again, delta P divided by L to the negative del P or del Z. You can change your Vmax in the quantitative dimension that you can measure from the experiment. So you will get your Vmax equal to 2V. So from here, you can compare what happened if you have a flow in circular tubes, what happened if you have a parallel tubes. For circular tubes, Vmax equal to 2V. For parallel tubes, for parallel plates, you have 2 over 3V. Okay, so maybe when it comes to a final exam, we just test your intelligence whether you understand what happened if the end user changed the type of the configuration of the pipe from circular pipes to fixed parallel plates. What happened to the Umax? So this one you need to able to relate to these two slides. You need to able to relate what happened to the Umax when you have a fixed parallel plates is a ratio of 1.5V. However, if you have a cylindrical pipe, the Umax only the Umax will be 2V. If you have a cylindrical pipe, the Vmax at the center will be higher than the parallel plates. These few slides explain all these phenomena. These few slides explain the phenomena. Okay, the next one is question 14. It is also the last few slides for this chapter. Again, this one you can read from my slides later on. I will just explain very fast. You can read from the slides. Try to understand the strategy to get the velocity distribution for circular tubes. So just now for circular tubes, we have our velocity profile, our parabolic equation just now. All right, you look back the previous slides, you will have this one. And we add a Umax with at the center here. You have this equation because R equal to 0. Right, you get this one. So if you get the ratio between Vz divided by Vmax, you take this equation, divide by this equation, you simplify the mathematical model because the constant value, the front is the same. So at the end, the ratio between these two, you get R squared minus R, capital R squared divided by minus R squared. You rearrange, you get 1 minus the ratio of R squared. You'll get this one. Okay, you'll get this one. All this from the Navier-Stokes equation. All this origin from the Navier-Stokes equation. Based on the assumption, we reduce to these two. Just a recap for laminar flow, our Reynolds number is below 2100. This information is very important for your test 1 and final exam. Okay, so we have done for chapter 4 already. We have covered chapter 4. So we have go through type of flow just now. And then we look at what happened in the circular pipes. What happened in the two parallel plates? What is the difference between these two? What happened to the Umax? How to get the parabolic velocity profile? Type of flow, we see the duplets, the sink, the source, all these. All right. Let me stop the recording.